So I'm going to be going over C.A.I.N.N, which stands for Christopher's Artificially Intelligent Neural Network. It is a deep learning framework that I built. It's built in C++ with a Python wrapper around it. It was designed to emulate Keras and other deep learning frameworks that you can find out there. So the source code for this project can be found on my GitHub. I'll put a link to it in the video description. Anyone is free to kind of pull this down and play with it. The only requirements you need to run this are Python 3 or higher and CMake. So I'm going to be demoing the framework and training a model on it using the C.A.I.N.N dataset. So this is a data set of 60,000 images of clothing of different types. Each image is a 28 by 28 grayscale image, which means it's a black and white image, and it's a pretty small one. There are 10 categories of clothing that these images can represent. Those include t-shirts, trousers, pullover dress, and the rest are listed here. So I pulled everything I'm going to need for a demo into a Jupyter notebook. I'll go through these cells one at a time real quick. So this first one's just to import some libraries in Python that we need. Second one is to load up the C.A.I.N.N dataset, which I have local on my machine right now. I'm going to take that data set and I'm going to pull out the training labels and the training data, split that up, and then I'm going to normalize each pixel in each image by dividing it by 255. Next, I'm going to split my data into training data and test data. We'll use the training data to actually train the model, and the test data we'll use afterward to validate how well our model is doing. I decided to split this up by taking the first 40,000 images of the data set and use those for training, and the last 20,000 we'll use as our test data set. The cell is just to kind of plot an image so we can see what that kind of looks like in more detail. And then we get to our framework. So to use our framework, we're going to have to import three things. One is the neural network itself. The second is the activation function, and third is we want to import loss to help us calculate our loss functions at the end. Then we get to actually telling the model how we want it to be set up, what we want each layer of the neural network to look like, and all that fun stuff. We start by instantiating a neural network object. Next, we're going to tell it to add an input layer. The parameter that we pass into this tells us what the dimension of each example in our training set is going to look like. In this case, as I said, for the C.A.I.N.N data set, each image is grayscale, so it only has one channel, and then has 28 pixels in width and 28 pixels in height. After that, since this is coming in 3 dimensions, as you know, these images tend to, we want to add a flatten layer, which will take the input and flatten it into one dimension that the rest of our neural network, in this case, can better handle. And then we start adding our hidden layers. We can do that for just a normal vanilla dense layer by calling this method add fully connected layer. The 2 parameters we would pass into this are how many neurons we want in each layer. So this first layer will have 500, the second layer will have 250, so on. And the second parameter is what kind of activation function we would like to use. So C.A.I.N.N supports a couple different types of activation functions. Those include sigmoid, ReLU, leaky ReLU, pass, and softmax. And then finally, we'll have our output layer. We're going to set this to 10 because there are 10 different categories each image in the C.A.I.N.N dataset can fall into. And then our final activation layer is going to be a softmax, which is good for categorical purposes. It allows the neural network to pick confidence intervals for each category based on each image. And then we can pick the highest confidence interval and say that's the one the neural network's actually picking. So we do support a bunch of different layer types. As you saw, the input layer, fully connected layer. We have the output layer. We do support an embedding layer. That's good for when you're processing text and you want to reduce the dimensionality for things like natural language processing. We also support a dropout layer, which is helpful when you are trying to keep the model from overfitting. So that'd be as simple as figuring out where you want the dropout layer to be. So yeah, I had a add dropout layer here. We're going to drop 10% of all the data that gets processed between this dense layer and this dense layer. Next, you're going to want to call this build function on the neural network. This is going to actually build and construct your initial weights within it. So there's a couple other things we can do if we want. We can set how often we want the neural network to print our loss. So if you have this set to 1, then after every iteration of training, it's going to print the loss. You can set that number to whatever you want. Another thing you can tell the model to do is to actually shuffle the training data between iterations. This will also help a little bit with overfitting. And then finally, we're going to set the learning rate on a neural network. Convention usually says anything between 0.1 and 0.001 is good. So I picked in between that. And then finally, we're going to call train on the model to get it to actually start training. Some of the parameters you would pass into training are the actual training data, the training labels. If you're training in mini batches, how large you want that mini batch to be. In this case, I passed 8, which means it'll train 8 images at a time. This is how many epochs we're going to do, or how many iterations through the entire training data set we're going to train this model on. And then finally, what is our loss function going to be? So we call that, as you can see, the model started training here. It just tells us how many epochs we have, batch size, and the input size. And then as you can see here, it already finished the first of our 3 iterations, and it told us that our loss was 0.27. After the second iteration, we can see that our loss went down to 0.18. This is good. Generally, a smaller loss means that our model is doing better and it's actually learning from our training data set. And we can also see that it's shuffling our data between iterations as well. So we're just going to wait a couple more seconds for the third iteration to finish. So we only told it to do 3. And you can see training is complete, and our loss after our third iteration was 0.16, which is good. So now on this block, all I'm going to do is take our test data, which the model has not yet seen, and I'm going to have it, the neural network or the model execute each image in that test set, and then we're going to see, we're going to count how often the model actually got the correct answer. So we're going to run that, and we'll see here that the model was accurate 83% of the time. That's pretty good considering, we only trained this for a couple of minutes. It's a small model, and it's also not a model that's optimized for computer vision, which is technically what this is, since it's categorizing images. This is a vanilla dense neural network. If we really wanted to do well on images, generally you want to use something like a convolutional neural network. So 83% is pretty good. If we continued to train this, we would most likely see the accuracy get even higher, up to about 95% is what I've seen with a model this small. So then all I have here is just demoing the model doing a couple of specific images. So if it takes this image and processes it, you'll see it outputs that it thinks the image is a t-shirt, and it's 98% confident in that answer. And the correct answer was that it was a t-shirt. Second time through with this image, the model thinks that it's trousers. It's 99% confident in that, and the actual answer was trousers. And then on the final one, The model thought that it was a shirt. It was a little less confident in this one, only 84% confident, but the actual answer was shirt. So it was correct on all three of these. Finally, one of the things you can do is when you are done training, you can hit this save function, and it'll save. Oh, sorry, it was right here. So you set your file path, and you can hit uh, the save method on here, and this will take your model and it'll save it into a file format that at a later date you can call load on it, and then you'll be able to load up that same model and then continue to use it at different times. So that's also supported by this framework. And that's largely it.